Good evening to all the participants. And today in that AMC course, that is Advanced Materials Chemistry course, in the Functional Materials subsection, what we are going to cover is batteries and supercapacitors, the second part, among energy materials. So we'll be covering a portion of the batteries we have already covered in the first lecture of this functional materials subsection. And today in the second lecture, we'll be continuing with batteries, followed by a little bit on the supercapacitors. So overview of whatever is going to be covered in this particular class. So in the last class, we had already talked about the cathode materials for lithium-ion batteries. So in today's class, we will be continuing with the electrode materials. So today we'll be discussing the anode materials for lithium-ion battery. This will be followed by how cell is prepared, then how you characterize these lithium-ion coin cells. The techniques which we will cover particularly are cyclic voltammetry, charging discharging cycles, and impedance spectroscopy. Then we'll follow it with a little discussion on battery life. And with this, we'll conclude our entire discussion regarding batteries, and then we'll move on to supercapacitors, where we'll be talking about electrochemical double layer capacitors, pseudo capacitors, and hybrid capacitors. And this will be followed by a short overview on fuel cells. So with this, let's first get into the mode of electrode materials for lithium-ion battery. So today we'll be talking about the anodes, and we know that lithium-ion battery, the anodes which are currently used in the commercial batteries are particularly graphite. So why graphite? Because graphite has an operating voltage which is very close to that of lithium-ion. It's almost 0.1 volt versus lithium-ion. And it has a capacity, that is a theoretical capacity of around 372 ampere hour per kg. So this is corresponding to the insertion of 1 lithium for every 6 carbon atoms. So what it results in when that intercalation or the insertion of lithium happens in graphite is it gives rise to something like LIC6. So that is why, because of this very, I would say, a nice capacity of 372 ampere hours per kg, as well as the operating voltage, which is almost close to that of lithium. So that is why graphite is considered as the best anode as of now, which is being used or already commercialized in lithium-ion battery technology. Now, if you look into the operating voltage and the electrochemical potential of this particular element, that is graphite, of the material graphite, what we see is the redox energy of graphite. It actually lies, as you can see, above the LUMO of your electrolyte window. Whatever commercially available electrolytes, what we are using right now in the batteries, this graphite actually is having its redox energy, which is lying higher than that of the LUMO. Now, if you recall, in the last class, we had already discussed that what is the ideal combination. So generally, we talk about anodes which are having their electrochemical potential, which is kind of lower than the LUMO. But in this case, it is a little bit higher. So obviously, what is going to happen is you will have some kind of degradation of the electrolyte happening. And that degradation of the electrolyte is going to result in the formation of your SEI layer, which is nothing but that stable solid electrolyte interface layer on the graphite. So in this case, though you will lose some lithium due to the formation of the SEI, what happens is, in this case, the formation of this SEI actually kind of gives us stability. Stability to this particular graphite anode for long runs. So it improves the cyclability because it prevents the exfoliation of graphite by the formation of this SEI layer. So this is one of the primary anodes which is being used in lithium-ion batteries. Now, if you look into this particular plot of capacity versus voltage, here I have shown you a few of these insertion chemistry based electrode materials and some conversion chemistry based electrode materials. So insertion based materials, as you know, we have already discussed graphite. There is another insertion based material which is also being used, and that is lithium titanate. So the redox energy of this lithium titanate, it is if you find the redox energy, if you see, it is actually lying above the LUMO. So what happens is, since it is lying in between the electrolytic stability window, as you can see over here, the electrolyte stability window. So what happens is in this particular case, if you are using this insertion anode, there is no formation of SCI. So if it doesn't form SCI, this is definitely one advantage because you are having minimum amount of loss of the lithium. And resultantly, what is going to happen is your initial Coulombic efficiency is going to be very high for this particular material. But the problem is that this particular material's operating voltage, if you see, it is right now over here. It is like 1.5 volt. Whereas in graphite, as we have seen, it is almost near to the lithium ion voltage, which is 0 volt. So in this particular case, you find it's around 1.5 volt. And as I have mentioned in my previous class, that your energy density is having a factor of that operating voltage coming into the picture. So in this case, because the operating voltage is very low, what happens is the energy density of this particular material, if you are using it in the battery, it gives a battery a very low energy density. And if it's a low energy density, then obviously you cannot use it for many things like portable electronics and all, and also for electric vehicles, but you can definitely employ it in cells for grid storage, which is basically the renewable energy storage. So because there the size is not a problem, so these kind of anode materials can be used for. Here I would just like to touch upon, though it is not in your syllabus, about the conversion chemistry. So there are few electrodes which are work on conversion chemistry. So here the anode materials can be oxygen, it can be sulfur, as you can see over here. And these are also falling in between the electrolytic stability window, and also these also doesn't lead to the formation of any SEI. But this we will not cover over here. So if you want to read, you can read it some extra. So here, with this, we are completing about the lithium anodes. These are the two main kinds of anodes which are there. That is graphite and the lithium titanate. So now we'll talk a little bit about the general structure, the effect the structure has on all the types of different electrode materials. So in structure, if we are actually moving to nanostructures or nanomaterials for the same electrode material, if it's in bulk form and if it's in the nanomaterial form, there are certain benefits associated with it. One of the primary benefits is the enhancement of the reversibility of the lithium-ion insertion and extraction reaction in the nanostructured anodes or the electrodes without destroying the crystal structure. So if you are having nanomaterial, then the insertion reactions can happen without destruction of the crystal structure. Comparatively, in bulk materials, the destruction of the crystal structure is more. Then obviously, because the size is less, then the diffusion or the transport distance of the lithium also decreases. And because there is a reduction in the transport distance, then what happens is basically your efficiency of the particular electrode material, it increases. And also there is a change in the site energy of lithium ions occupying the post lattice. So this affects the electrochemical potential of the electrodes. Because if you move into the nano form, what happens is there is a change in the site energy of the lithium. So that also kind of affects the electrochemical potential of the electrode. So definitely, how the structure of the material is, your electrode material is, it definitely affects the performance of your overall performance of your battery. Then defects on the electrochemical potential, the effect of defects on electrochemical potential of electrodes. So now these defects in this particular material, in any material you are using, it can be introduced either through doping or through atmosphere treatment or control of synthesis methods. So what happens is generally alien atoms or dopant atoms, they will replace the inherent atom, whatever was there in your original material, and it will produce either cation or anion vacancies. So this affects the electrochemical performance of your electrode. And why this happens? Because of the presence of these cation or anion vacancies, what you have is a modified chemical pressure. You can also have lattice distortion. You can have change in the crystal field, and all this is kind of going to affect the efficiency of your electrode material. So here I have shown an example. If you look over here, this dark line over here, which is a plot of specific capacity versus the potential for normal V2O5 electrodes. So here you see the capacity is somewhere less than that of 250 milliampere hour per gram. The moment you are doping in nickel, you find that the specific capacity is increasing to almost 300. So what is happening in this case? This lower valence of nickel in place of high valence of vanadium. Vanadium is having a much higher valency compared to that of nickel. So it effectively decreases the electrostatic repulsion between the cations. So whatever electrostatic repulsion is there, it kind of decreases because now nickel is having a lower valence. And so it decreases the lithium site energy. and it increases the potential of the doped material. So the energy density and the capacity kind of increases when you are doping nickel in vanadium site in V2O5. So this is how defects can actually play a role in changing the electrochemical potential of the electrodes. Then mesoporous materials, not nanomaterials, these are mesoporous materials. So definitely they have a lot of pore structures. That electrode material is having pores. So how does the pore structure help? If you are having an electrode material with a lot of pores inside, it is conducive to the full infiltration of the electrolyte. So an electrolyte is able to get into all these different areas of the electrode material, which will not be possible if you are having a solid bulk material. So this again reduces the migration distance of the lithium ions. So it facilitates the lithium ion exchange across these interfaces of, that is the electrode-electrolyte interface. And it is also because there is a pore structure, there is some kind of space available. So it can tolerate large volume change of the electrodes when the lithium ion is getting inserted or when it is getting extracted. So that is why this is again conducive. In some cases, it is highly conducive when you're having pore structures in the electrodes. But here one point you have to remember is, if it is extremely porous, then it can also lead to some kind of disadvantage. And what is that disadvantage? The disadvantage is it will lead to the formation of a larger amount of SEI. So if a larger amount of SEI forms, in that case, what is going to happen? You will lose your lithium ion in the formation of this SEI. So your initial Coulombic efficiency is going to decrease. So basically, this is kind of a antagonistic thing, that you need porous material to improve the storage kinetics and structural stability, but at the same time, you did not need that much pores, so that it kind of gives a disadvantage by forming a very huge amount of SEI, leading to the loss of lithium. So you have to strike a balance between the two, and that is what generally researchers do when they are finding out new electromaterials in the lab. So what is the current status of LIB currently? The commercial lithium-ion technology is largely limited to cells, which is having a gravimetric energy density of less than 250 watt-hour per kg. The volumetric energy density ranges is less than 650 watt-hours per liter. So what the target is to go up to at least 500 watt-hour per kg, or greater than the volumetric density should be greater than 1000 watt-hours per liter. And how are you able to do that? How the research is progressing in this field? So you have to increase the cell voltage. Why? Because the only option is why to increase the cell voltage, because and the cell voltage not of the anode, cell voltage of the cathode. The reason is because anode anyway with graphite you are having something which is very close to that of lithium ion. So there is no point in playing around with the anode that much. But definitely the cathode voltage can be increased so that you have a higher energy density. So the cathode surface with an operating voltage of greater than 4.3 volt, currently it is not stable with the organic solvents which are being used in the electrolytes. The organic solvents which are normally used in the electrolytes currently are ethyl carbonate, diethyl carbonate. So all these solvents, they are kind of unstable when you are having a voltage of more than 4.3 volts because it is going to degrade. So there are certain candidates which has been identified which has very high operating voltage, like you have spinel LIMN 1.5, Ni 0.5, which is having a voltage of operating voltage of 4.7 volt. Then you have olivine structure, lithium cobalt phosphate, which is around 4.8 volt. And then you have LINNC, which is having an operating voltage again of greater than 4.3 volts. To reversibly insert and extract more lithium. But obviously, the electrolytes are not supporting this kind of high voltage. So currently, you have to look for new liquid or solid electrolytes with desired characteristics, which will enable the utilization of these high voltage cathodes. So that is one of the ways in which you can actually improve the energy density of LIBs. Then, of course, you can also increase the charge storage capacity. How you can increase that? This is normally limited currently in the insertion materials. It is limited by the number of crystallographic sites which are available for the reversible insertion and extraction of lithium. However, as I mentioned, the conversion anodes or the conversion reaction electrodes, do not suffer from these kind of limitations. So what you have to do is you have to look into conversion anodes, but the question might be that why currently we are not using it, because there are again certain disadvantages associated with the use of conversion anodes. And one of the primary disadvantages is the huge volume change which occurs when basically conversion anodes are being used or conversion. What happens is almost you will get a volume change of around 400% compared to the original size of the electrode, and it is very difficult to have materials which can accommodate that much amount of a volume expansion. So the electrode material will kind of it is going to peel off from the current collector, and your battery is going to degrade very fast. It is just not going to undergo. It's not going to show good cyclability. And then what happens is, even if it stays for a few cycles, then the pulverization of the particles take place. Then if it is pulverized, then the surface area is increasing, so you'll have a lot of SCI formation. So a lot of your lithium metal is going to get trapped, lithium ion is going to get trapped, and obviously you will lose capacity. So you lose lithium metal, so you lose the capacity. So what you can do is you can reduce the particle size to nano size, or you can deliberately leave space within the active materials in the conversion anodes to take care of this volume expansion. But the problem is that it is going to lead to a lot of formation of SEI, and it is going to decrease your volumetric energy density. So currently, to improve the charge, what is being done is to add a few percent of silicon into graphite. So it is improving the capacity to some extent. So that is the only change as of now that has been done. So a lot of research is still left in this field. So currently, where is the lithium-ion technology headed? So as I said, though the technology which is currently based on insertion reaction cathode and anode is going to continue in the foreseeable future, despite the limited energy density we are seeing, which is dictated by the number of crystallographic sites available, as well as the structural and chemical instabilities at deep charge. This is still, as of now, the best combination we have. But conversion reaction anodes as well as alloy forming anodes can be used to improve the capacity. You can have again, lithium metal as anode and replace the liquid electrolytes with solid electrolyte that can offer safer cells with a higher operating voltage and charge storage capacity. But the practical viability is yet to be ascertained. So currently, from all that we went through in the last lecture as well as up till now, you can see the feasible near-term strategy will be to focus on high nickel layered oxide cathodes, liquid electrolytes, which is compatible with and forming stable SAI on both the graphite anode as well as high nickel cathodes. Innovation in cell engineering to fabricate thicker electrodes with lesser inactive components, and novel system integration to realize safer, longer, long life and stable batteries. So currently, what we have to look into is LINMC type of cathodes. You are having electrolytes which are able to sustain this kind of high operating voltage. You can have graphite as anode, or else the other combination which is possible is you can have lithium metal only as the anode, but you change the electrolyte from liquid electrolyte to a solid electrolyte. So the usual process over here, the same whatever I said in the last slide, the same thing is shown here pictorially. So here you have the usual process of insertion materials. So you have a low capacity, whereas you can have alloying materials also. These are commercialized and they are having high capacity, but volume change is still an issue for these alloying kind of materials. And under development is the conversion-based anodes and cathodes with a large capacity, and they do have a voltage hysteresis. So parameters which now needs to be considered in adopting lithium-ion batteries for various applications. If you see the energy, power, charge discharge rate, cost, cycle life, safety, environmental impact. So in electric vehicles, as you see, energy density is very important. Cost, cycle life, and safety are important, but energy density is really important. For grid energy storage, energy density is not that important. Cost, cycle life, safety are equally important. In portable electronics, again, energy density plays a very important role. So as we can see that energy density, as we improve for lithium-ion batteries, it is going to play a very critical role for electric vehicles and for portable electronics. But for the other kind of electrode materials, where basically the capacity is not really much, as well as you can see that the operating voltage is not much for those electrode materials, they can again have application in grid energy storage. But one thing which you should remember is that it should have a fast Sorry for that interruption, but what we can see from as we were discussing the parameters that needs to be considered in adopting lithium-ion batteries. The thing is that it is desirable to have a fast charge discharge rate for all the applications from electric vehicles to grid energy storage as well as portable electronics. So now we have the electrode materials. The next stage is obviously how to fabricate a coin cell. So as you can see over here, what happens is you have the electrode materials, but normally you have to have certain additives because that electrode materials needs to be pasted on top of a current collector. So generally copper or aluminium current collectors are used depending on whether you are fabricating an anode or a cathode. So what you have to do is you need to have a binder. The binder is generally PVDF. The solvent is generally NMP. And then on that, you add a little bit of conductive carbon. You take your active material, you make a slurry out of it. And then you can see that with a Doppler blade, what you can do is you can actually make a you can coat this particular slurry, whatever you have formed, on the current collector. And with that, either you can use a Doppler blade or you can use a slot die or you can use a sprint printing technique. And then, of course, you have to do calendaring of that particular current collector with the electrode pasted on it. Then you dry it. And after that, you have to kind of place those particular electrode, that is the anode or the cathode materials. Either, you have to assemble it in the form of a coin cell. So how that assembling happens is shown over here. So this is generally the layout of a CR2032 coin cell. So here in this case, what happens is you have a negative case, you have a wave spring, you can see a spacer. Then for the cathode material, so this kind of disc you will have when you place the disc. You have a separator, then you have a lithium reference over here, then you have a graphite anode followed by a positive case. So this entire thing goes in, you have to clip it, and after clipping it, then your coin cell is ready. So with this now, all the different characterization techniques are set to be done. So what are the different cell characterization techniques we'll be discussing in this particular class? As I mentioned, it will be cyclic voltammetry, that will be followed by your impedance spectroscopy, and also charge discharge cycles. So if you look into any kind of battery related work, these are the primary 3 cell characterization techniques which are reported. So I thought that in this particular class, we should cover all these different cell characterization techniques. So now, cyclic voltammetry, this is generally commonly employed to investigate the reduction and oxidation processes of molecular species. So this is an invaluable technique to study electron transfer initiated chemical reactions. So now there are 2 different conventions by which actually you show, you plot the current versus potential. So in the US convention, what you do is you move from high potential to low potential, and you have reduction at the top and oxidation at the bottom. The IUPAC convention, generally it is from low potential to high potential, whereas the oxidation is depicted in the top as well as the reduction is in the bottom. So you start from reduction in both the cases and you go up to the oxidation. Excuse me. The arrow indicates the beginning and the sweep direction of the first segment of forward scan, and the caption indicates the conditions of the particular experiment. So now here I'll show you what happens for a simple reaction, like when you're reducing ferrocenium ion using cyclopentadienide, abbreviated, this is abbreviated as Fc plus to ferrocene. So ferrocenium ion is moving to ferrocene. So basically a reduction reaction is happening. And this is the CV you have obtained when you are running this particular reaction. So what happens? So all these small graphs, that is A, B, C, D, E, F, G, it is actually showing you the concentration profile in these different regions of the cyclic voltagram, which is shown over here. So the concentration profiles for Fc plus is given in blue, as you can see. and that of Fc, that is ferrocenium ion, is blue and ferrocene is green. So at the starting, that is at point A, you are having mostly Fc plus, that is ferrocenium ion. So you can see the concentration is highest, whereas you are having zero concentration of Fc. But as you move to point B, you can see that there is a buildup of the concentration of the ferrocene, whereas there is a decrease in the concentration of the ferrocenium. And this D is basically the distance from the electrode. So from the electrode surface to the bulk solution, this distance is given as D. So with this, you can see how at different points this concentration is changing. So the ferrocene as well as ferrocenium ion, the concentration keeps changing. And accordingly, you can see in the cyclic voltameter, there is a peak coming in. So there is a state where a high current is coming in. And then there is a state where there is a low current coming in. And how to explain this? So why there are peaks in the CD plots? So this equilibrium between this ferrocenium and ferrocene is described by the Nernst equation. Nernst equation we had already discussed in the first class. So if you are applying this Nernst equation to this one electron reduction for the ferrocenium ion to ferrocene, the activities here in this case are replaced by concentration, which are obviously more experimentally accessible. And the standard potential, what you have over here, is generally replaced by the formal potential. How you get the formal potential, that I'll discuss. So the formal potential is nothing, it is specific to the experimental condition employed, and it is often estimated with the experimentally determined E half value. So if you look over here, this is the E half value in the diagram, as you can see. This is nothing but your formal potential, and this is more experimentally accessible. So when the potential is scanned during the CD experiment, the concentration of the species in the solution near the electrode changes over time, and this change is according to that of the Nernst equation, as predicted by the Nernst equation. So now if we look into the volume of the solution at the surface of the electrode containing the reduced ferrocene, this is called the diffusion layer. Now this is going to continue to grow throughout the scan. So what happens is, when it reaches this point, you are having the maximum amount of this ferrocene form. Now, this is actually preventing the ferrocenium ion from the bulk to get transported to the electrode. So, ultimately, what happened? That upon scanning to more negative potential, that is on this side, the rate of diffusion of these ferrocenium ion from the bulk to the electrode surface becomes lower. So, it results in a decrease in the current. And as the scan continues, you can see, so from A to C, you see an increase in the current, and from C to D, there is a decrease. So this, whatever Fc is present at the electrode surface, this gradually again during the oxidation part of the cycle, what happens? It gets reduced, it is getting oxidized to Fc plus as the applied potential is becoming more and more positive. So at points B and point E, look, the concentration of Fc plus and Fc at the electrode surface, they are equal. This is according to the Nernst equation, because E is equal to E half. So this corresponds to halfway potential between the two observed peaks, that is the two observed peaks are C and the point F. And this provides a straightforward way to estimate your E0 naught value, which is nothing but your action potential value or a reversible electron transfer. So why these two peaks are separated? This is due to the diffusion of the analyte and from the surface of the electron. So this is basically the general concept of CD. So now if the reduction process, whatever we are seeing, it is both electrochemically as well as chemically reversible, then the difference between this anodic and the cathodic peak potential or the peak to peak separation is around 57 millivolts. This you get from the Nernst equation. And the width at half max on the forward scan of the peak is 59 millivolts. So whenever there is a low barrier to the electron transfer, that is when we say that there is an electrochemical reversibility, this equilibrium, the Nernstian equilibrium, established immediately whenever there is a little slight change in the potential. However, if there is a large barrier to the electron transfer, that is, there is an electrochemical irreversibility associated with the particular reaction, then the electron transfer reactions become sluggish or slow, and the more negative potential will be required to observe the reduction or the oxidation reaction, as the case may be, and it will give rise to a larger value of this delta E. So these are the few points which you have to remember when you are working with CD. Now, whenever we require, when we record a cyclic voltammogram, what happens is we apply a scan rate. Now, the scan rate is very important. So the scan rate of this experiment, it will control how fast the applied potential is scanned. So faster scan, what it is going to do, it is going to decrease the size of the diffusion layer. And the moment the size of your diffusion layer is decreased, higher currents will be observed. Because right now, then the movement of your ions from the bulk to the electrode surface, it will have to encounter less amount of the diffusion layer. So it is going to be easier. And so you will see a higher current. Now there is one particular equation known as Randall-Serig equation. And this is for electrochemically reversible electron transfer processes, which involves freely diffusing redox species. So here this IP is nothing but your current, which is generated, the peak current. And this actually, if you see, it increases with the square root of the scan rate. The scan rate is given as mu, and this increases with the square root of the scan rate. So here N is nothing but your number of electrons which are transferred in the redox event. Your F is the Faraday constant. A is given in centimeter square, and it is the electrode surface area, generally the geometric surface area. And then you have obviously your D0, which is the diffusion coefficient of the oxidized analyte, the diffusion coefficient of the ions. In case of lithium-ion battery, it's the lithium ions which are moving in. And C0 is the concentration, the bulk concentration of your analyte. So this particular peak current is related to the scan rate by this particular equation. This is known as the Randall-Serig equation. So now in a reversible process, so this is the equation of voltammetry for intercalation reaction. The intercalation reaction is what is happening when you are having a lithium-ion battery. So in a reversible process, since the rate of electron transfer is rapid enough at the surface of the electrode, the peak potential is independent of the variation of the scan. So EP minus EP half, this is nothing but 56.5 millivolt at 298. However, if it is the reversible, if the process is quasi-reversible, so which shows limitation of the electron transfer kinetics, now then the peak potential, it becomes a function of the scan. Now lithium-ion intercalation reactions, it tends to follow a quasi-reversible process because the cathodic and the anodic peaks we have seen, they are dependent on the scan. So the CV of the quasi-reversible process, it shows gradual peak shifts to higher potential value whenever the scan rate is increased. And this is generally is not observed in case of a reversible process, and this happens due to the presence of further amount of over potential in a quasi-reversible process. So now we'll talk particularly about CV of lithium intercalation. So now if you want to obtain exact lithium-ion diffusivity, that is very important when you are testing any electrode material, two boundary conditions should be considered according to the scan. One is a fast scan rate when you're having a semi-infinite diffusion process. In that case, you have an equation which is similar to that of Randall-Serig equation. Whereas if you have a very slow scan rate, in that case, the diffusion process is finite. And in this case, you know, the peak current will become proportional to the scan. So IP is directly proportional to mu. So now these are these two boundary conditions in which the lithium-ion diffusivity have to be calculated in case of a lithium-ion battery. So if you want to consider it at any kind of scan rate, then this is the general equation which is given over here. You can see. So here, you need not remember the equation, but please see that N is again the number of electrons transferred in the redox event. And this beta value is nothing but Nm mu I squared by d RT. I is here the distance of electron, and F is obviously the Faraday constant. And you also have a factor which is this beta factor, which takes into consideration both this fast as well as slow scan rate. So you have both the boundary conditions which are satisfied in this particular equation. So by using this equation, you can calculate it for any kind of scan rates. So now, in batteries, when we are testing the lithium-ion coin cells, the electrochemical reaction occurs in the electron consecutive processes. So in this case, the current which you obtain, it actually obeys a power law. I is equal to A nu to the power of. Now I is the current A, nu is the scan rate as I have repeatedly said, and A and B, these are adjustable values. So what is B? B is the sum of the Faraday, that is diffusion control, and non-Faraday, that is capacitive current. Please remember, whenever there is a non-Faraday current, we need something which is not diffusion control, something which is not redox control. So B is nothing but the sum of both Faraday, that is diffusion controlled, as well as that of non-Faraday, that is capacitive currents. So if only diffusion controlled reaction, the observed current is proportional to mu to the power of half. So it is basically the square root of your scan rate. And this follows the Randall-Sepsky equation. And capacitive current, which is also known as non-Faraday or double layer current, this is directly proportional to the scan rate. So the capacitive current, you have to remember, is dominantly measured at a fast scan rate, whereas the diffusion controlled current is dominantly measured at a slow scan rate. So how will you get the B value? So now with this equation, I have already said what you do is you take the log on both sides, you rearrange it, and if you are plotting log I versus log mu, what you get is the slope of this particular plot is going to give you the B. So now how do you estimate? Now when you have an electrode material, you have to find out that whether, how much of that current, whatever you are seeing, is coming from capacitive control current and how much is coming from diffusion. So for that, you have this particular equation. As I said, one of them is directly proportional to mu and the other is proportional to the square root of mu. So again, you see I is equal to, you take constants K1 and another constant K2. You rearrange this equation, and if you are plotting this scan rate, mu to the power half against I by mu to the power half, what happens is slope, what you will get is this particular K1 value. So once you get the K1 value, you can put it in the equation, you can get the K2 value. So K1 mu is going to give you the current attributed to capacitive reaction, and K2 mu to the power half is going to give you the current which is attributed to the diffusion control reaction. So this is how you generally use cyclic voltammetry for assessing the quality of your material. So now your voltammetric, the plots you obtain, it also gives you a lot of idea, about how these, by looking into the voltammeter, you can actually make out how your electrode material is. There is a lot of effect on the shape of the CV plot depending on various factors. So one of them is the particle size. So what happens when you actually plot it with the particle size, you find that suppose I am plotting LiFePO4 nanoplates. So I am using electrode material LiFePO4 nanoplates and microplates. So the nanoplates you will find is going to give you a higher current compared to that of the microplates. Why? Because size reduction induces an increase in the interfacial area of the particles, that's the contact area with the electrolyte, and it shortens the diffusion length of element. So find current is much more. So as a result of enhancement in kinetics of redox reaction, the overall peak current increases at the same scan rate in the CV plots. So you can see that as you decrease the size, the current value increases. Then the shape of the CV plots also depend a lot on the electrode thickness as well as on the scan. So if you have a thin electrode condition, then the entire portion of this electrode is in uniform state and electrochemically active. So what happens, the peak split changes, they are not so large. So this means that both the surface and the bulk structure of the electrode, they have a uniform potential and they are homogeneous. But whenever you have a thicker electrode, the scan rate increases. With the scan rate increase, you will see there is a much larger peak shift. So at the peak split, if you see over here, it is much larger compared to what you see in case of a thin electrode. Why? Because the lithium ion diffusion from surface to the bulk now becomes more difficult. So there is going to be a lot of overpotential again all over here. And that's why you will find a lot of peak split, which you will not see in case when the electrode is thinner. So these are some of the factors which affect the shape of the CV plot. Then temperature is another very important factor which affects your CV plots. So the peak current which is arising from a diffusion controlled reaction, this is affected by the operating temperature. But if you have a capacitive contribution to the current, that is again not affected by the temperature. So suppose if you see with temperature, there is lot of shifting in the peak current, we should immediately make out that this is basically a diffusion control. Whereas if the change is negligible, then in that case, it is the capacitive contribution which is playing the larger role. So the rate of this electrochemical reaction, it depends on lithium-ion diffusion in the lattice of the active materials. And this diffusion process is basically temperature sensitive. So when the peak split decreases at high temperature, it indicates that the rate of the electrochemical reaction becomes faster and the corresponding redox peaks can appear earlier. So as you see over here, when you're moving from 30 to 50 degrees centigrade, what is happening is the difference in peak position decreases. So that means it's the diffusion process. So now this is about the CV. So now again we are refreshing a little bit of the definitions which we did in the first lecture. So terminal voltage, if you remember, it is the voltage between the battery terminals when the load is applied. Open circuit voltage is voltage between the battery terminals when no load is applied. Internal resistance is overall resistance within the battery, which varies with charge level and temperature and generally differs with charging or discharging. Then internal resistance of a battery, if it increases, then what happens? The battery efficiency decreases. So all this extra charging energy, it is going to get converted into heat. Battery capacity is nothing but the amount of electric charge it can store in a specific condition. And this is again measured by discharging a fully charged battery to a load at a constant current rate. And the capacity of a battery usually depends on the discharge condition. That is the discharge current rate, temperature, etc. Why I rehashed all these different definitions is because whenever you have a coin cell prepared, you have to do something which is known as GDC testing, which is basically galvanostatic, discharge, and charge testing. So here what you do, as and when you are charging the battery, what happens? The voltage, it increases. So during this step, what happens? Lithium ions are extracted from the cathode and they intercalate into the anode's graphite rings. So what do you do? The cell is potential static and held at 4.2 volts. So here we are doing with the cathode. So what is happening? The cell, it will be held at 4.2 volts. And after reaching the upper voltage limit, so this step will last until the current of it, it decays and it reaches around 0.4 milliamperes, which is corresponding to a C rate of 0.0. So this kind of ensures that your battery is fully charged. And the battery state of charge in this is 100%. So what we are doing essentially is a typical charge and discharge curve of a coin cell is shown in this particular plot. So voltage is basically these darker lines, as you can see, and current is these lighter lines. So they are plotted versus time. In this particular cell was charged and discharged with a current of 40 milliamperes, and the voltage range is between 2.75 volt to 4.2 volt. So what you are doing, first you are kind of increasing the voltage, holding it at 4.2 volt, allowing the current to drain back for around only 0.4 milliamperes. And then when this current is draining back and your voltage has been raised, your battery is fully charged. Then you go for a discharge. The voltage initially, if you find, it will drop. This is the IR drop you see over here. And this is directly proportional to the equivalent series resistance. So you see a drop in the voltage. And when the battery starts discharging, you will find the voltage again dropping. And when it drops very drastically, then you stop it because the discharge is complete in this case. And here is generally for this particular battery, we're stopping it at 2.75 volt according to this CDC curve. So this ESR, what I mentioned, it sums up the resistance from this voltage drop you see over here. It sums up the resistances from electrodes, electrolyte, and electrical contacts. The lower the voltage drop, the higher is the maximum output energy E that can be drawn from the battery. So the limit of a battery's usable capacity is reached when the voltage declines sharply, as is shown over here. And the discharge step is stopped at 2.75 volts. So at this potential, the state of charge is defined to be 0%. And the depth of discharge for this particular point is around 100%. So for the battery, we keep on discussing C rate. So C rate actually is basically how fast a battery is charged or discharged. So the battery which was used for this application have a rated capacity of 40 milliampere hour and the rate is 0.2 C. So this means for 5 hours, you can draw ideally 8 milliampere of current from this one. So for this particular battery, for whenever we say we are having a capacity of 40 milliampere hour and the C rate is 0.2 C, then it essentially means that for 5 hours or every hour you can take in 8 milliamperes of current from this particular battery can be drawn. So another important point is basically your cyclability studies. So a battery cannot just run for one cycle and then drop dead. It has to run for several cycles. As you know, when you're charging your mobile, your battery, if it is draining off after one cycle and then it doesn't charges again, it's of no use. So how many times the battery can cycle? That's a very important quality. And this is generally done by repeating this continuous charging and discharging. So what the initial charging and discharging I showed in the previous slide, this you continue for several cycles. So whenever you have a new material and you have prepared a coin cell, you put it for cyclability test and you see how the capacity holds. So this is basically each and every point is basically for discharge and charge of the battery. So one discharge and one charge is given as one particular point over here. So 1 point for discharge and the other point is for charge. So how the capacity is holding is very important. If your battery shows something that it is discharging in this way, your charge discharge values is dropping down severely, then that particular coin cell is of no use to you or the battery is of no use to you. So it has to hold on to that capacity of charge and discharge for at least 1,000 to 2,000 cycles. In the present case for lithium-ion batteries, it goes up to almost 4,000 to 5,000 cycles. So these are the preliminary tests you need to run for your coin cell. Now all this is to see how efficiently your coin cell is functioning. But now how to know what essential processes are taking place inside the battery. So for that again we have something which is known as electrochemical spectroscopy. So this is a non-destructive route for to in situ analysis of the dynamic processes which is taking place in the battery. So whenever you are discharging and charging a battery, dynamic processes are taking place because your lithium ion is moving from the cathode, getting inserted into the anode, moving through the electrolyte, and then again when you are discharging the battery, it is moving from the anode, it is going and again taking back its place in the cathode material. So all these dynamic processes you can access using this particular technique, which is known as electrochemical impedance spectroscopy. So this basically provides a lot of information in a relatively short space of time while preserving the integrity of the battery. You need not open the battery and then test what has happened. And then in EIS, what do you do? It's a small alternating current signal is applied over a very wide frequency range and you measure the response of the battery. So EIS is particularly sensitive to systems that contain several impedance elements, including bulk components and interfaces, which makes it well suited to study a multi-component device, which is a battery. So different components and processes, you have to remember within a cell, it operates on different time scales. So they have different time constants and can be separated in the frequency domain using this kind of electrochemical impedance spectroscopy. So if you look into an electrochemical impedance spectra, it looks somewhat like this, and each of this region actually can be it can be modeled on the basis of some electrical circuit, and this equivalent circuit is shown over here. So by looking at the circuit and by looking at this particular spectra, you will be able to understand with a little bit of understanding what exact processes are taking place inside the battery under dynamic conditions. So, but before we understand what the spectrum looks like, a little bit of background is important. So here we'll talk about Ohm's law. So as you know, it defines the resistance in terms of the ratio between voltage and the current. So R is equal to E by I. But you have to understand the relationship is limited to only one circuit element, which is the ideal resistor. An ideal resistor, it has several simplifying properties. So it follows Ohm's law at all current and voltage. Its resistance value is independent of frequency, and AC current and voltage signals for resistor. You have to remember these are in phase with each other. But in real life, life is not simple. So in the actual resistor, what we have in real life, they generally show much more complex behavior. So then instead of resistance, the term which we normally use is impedance. And this is a more general circuit parameter. So impedance is also a measure of the ability of the circuit to resist the flow of electric current. But unlike resistance, impedance is not limited by that Ohm's law properties or the simple properties which we discussed in the previous slide. So this is, as I said, the electrochemical impedance is usually measured by applying a small alternating current potential to an electrochemical cell, and then you measure the current which is passing through the cell. So suppose you apply a sinusoidal potential excitation. So the response to this potential is going to be an AC current signal, and this contains the excitation frequency as well as its harmonics. And this current signal can then be analyzed as a sum of all the sinusoidal functions, and this is known as a Fourier series. So electrochemical impedance is normally measured using small excitation signal. And this is done so that the cell's response is pseudo-linear. In a linear system, what happens? The current response to a sinusoidal potential will be a sinusoidal at the same frequency, but it is going to be shifted in phase. So remember, when you are having only a normal simple resistance, in that case, you have no phase shift. Whereas when you are talking about impedance in a real life circuit, what happens normally, what you see is a shift in the phase. So the excitation signal expressed as a function of time has a form. Et is E0 cos omega t, where omega is nothing but the radial frequency, and it is related to normal frequency by omega equal to 2 pi f. I'm rushing a little bit because I know that this is generally a rehash of things which you already know. So EIS can be used either in a constant voltage mode or in a constant current. But normally what we do is we use it in a constant voltage mode. So the current will respond at the same frequency as the applied voltage, but it is going to be shifted in phase. So in order to ensure a steady state, this EIS, this is important, is carried out using a small potential static signal amplitude of generally 10 millivolts, so that the cell's response is either pseudo-linear or linear. If the system is non-linear, then the response contains harmonics of the input signal frequency also. So if you want to accurately perform EIS on a cell during cycling, you must have a rest or open circuit voltage period is applied so that the cell voltage does not vary significantly during measurements. So additionally, another rest period should be given when you have already applied and the cell has already acted on this particular alternating signal. So when you are asking it to again record, in that case you must give another rest time, because you must allow that cell to recover from whatever dynamic processes it has undergone due to the perturbation which you have provided on the cell. That is very important. So rest period is very important. So now coming to your how exactly it is done. So this particular slide I have already explained that how you have ET and then how this is related, how the radial frequency is related to frequency. So now in a linear system, the response signal is IT and this is shifted in phase. So when you are having EP applied, then the IT is nothing but whatever the current what you are getting is I0 sine omega t plus phi. So what is this phi? So this is basically the shift in the phase. So if you are kind of expressing impedance in the same way as you express resistance using Ohm's law, then you will write ZT is equal to EP by IT, which is nothing but E0 sine omega t divided by I0 sine omega t plus phi. And then you have this particular expression Z0, that ZT time t is nothing but Z0, which is impedance at the 0 time, and when you have not applied the perturbation, with sine omega t divided by sine omega t plus your phase shift. So this is one way of expressing your impedance. But there is another way also where you are using Euler's relationship. Euler's relationship exponential J phi is cos phi plus J sin phi. So in this particular case, the impedance, if you are representing it as a complex number, then this ZT can be written as Z0 exponential J phi, which is Z0 cos phi plus J sin phi. This is important. So now, this is nothing but the real term, and this J basically is square root of -1, which is nothing but your imaginary term. So a generated impedance spectrum, it consists of a resistive term as well as reactive components. And the resistance is made up of a combination of electronic as well as ionic resistance. So the most common form of plotting impedance data is a complex plane plot of this imaginary part against the real part on linear scale, and this is known as a Nyquist plot. So presenting data in this way displays the resistance along the x-axis and the reactance, including the capacitance, along the imaginary or the y-axis. So as I now go further into the other slide, this will become more and more clear. So if you look into this expression above, the expression for Z omega is composed of a real, as you can see, real part as well as an imaginary part. So now in the Nyquist plot, we are plotting this real part as x-axis, the imaginary part as y-axis. So on this Nyquist plot, the impedance can be represented as a vector, you can see over here, of length, which is Z. So the angle between this vector and the x-axis is called the phase angle, which is phi. So Nyquist plot, please remember, has one major shortcoming. It is not able to show you at what frequency basically you are seeing this particular point. And so you will not be, from the data plot, you are not able to look up at what frequency it is. But you have to remember this thing, that it basically starts from a very high frequency, moves to a low frequency. So Nyquist plot, the origin is basically a very high frequency region, and the plot, the point where it is cutting on this particular x-axis, is nothing but a low frequency region. So the semicircle is characteristic of a single time constant. So for a single time constant, this one particular semicircle you are going to see. But mostly when you are recording EIS spectra for the different points, is you will never find such complete semicircle. It will generally move away from, it will come up to here probably, and then it will move on. So why it is? But before we go to the details of Nyquist plot, there is one more type of plotting which we can do, which is known as the board plot. So the impedance is plotted with log frequency on the x-axis, and both the absolute value of impedance and the phase shift you can plot on the y-axis. So now the board plot is advantageous. Why? Because from this you know at what frequency you are getting each and every point. You are getting the phase shift at whatever frequency it is applied, you are also getting the impedance value. So that is why board plot is a little more advantageous. But normally for LIVs, we generally talk mostly about the Nyquist plot. So now the EIS data, whatever you obtain, is commonly analyzed by fitting into an equivalent electric circuit model. So there are certain circuit elements you need to know about. One is the resistor. So the impedance of a resistor is independent of the frequency, has only a real component. Because there is no imaginary impedance, the current through a resistor is always in phase with the voltage. Then you have something which is known as inductor, and it is represented in this way. The impedance of the inductor, it generally increases as the frequency increases. Inductors only have an imaginary impedance component. So inductor's current is in phase shifted with 90 degrees with respect to the voltage. So you have a plus 90 degree shift with respect to the voltage. In case of a capacitor, the impedance versus frequency behavior of a capacitor is just exactly opposite to that of an inductor. So basically impedance, it decreases as the frequency is raised for the capacitor. The capacitors also only have an imaginary impedance component. So the current through a capacitor is in phase shifted minus 90 degrees with respect to the voltage. Then you have something which is known as Warburg impedance, which is given in the form of this W. So this is corresponding to the resistance due to mass transfer, that is diffusion control. So the impedance depends on the frequency of the potential perturbation. At high frequencies, the Warburg impedance is small, since diffusion reactants don't have to move very far. But at low frequencies, the reactants have to diffuse further, increasing the Warburg impedance. So generally on a Nyquist plot, the Warburg impedance, it appears as a diagonal line with a slope of 45 degrees. That I will show in the coming slides. And then you also have something which is marked as a constant phase element. Capacitors in these EIS experiments office, they do not behave ideally. They do not behave like ideal capacitors. So they act very much like a constant phase element, and this is generally used to model very imperfect capacitors. And they generally exhibit a 80 to 90 degrees phase shift. So now you have these equivalent elements and how the impedance impedance is represented. This is given in this particular table. You can go through it later. You look into the slides. So Z is equal to R in case of a resistor, whereas in case of a capacitor, you can see Z is equal to 1 by J omega C, which is C is nothing but the capacitance. So now, whenever you find an electrochemical cell, you cannot use a single circuit element to do it. You cannot use a single equivalent circuit to model that entire EIS spectra which is coming in. So you will have impedance in series, you will have impedance in parallel. So you have to remember that generally, mathematically, the simple formulas can be used to actually add up impedance in series or as impedance in parallel also. So resistance and impedance, they both go up when resistors are combined in series, whereas when you are connecting them parallelly, sorry, this I have mentioned as series, but it should be parallel. So the impedance will go up, but the capacitance will go down when these capacitors they are connected in series. So they are connected parallel. So the common equivalent circuit when you are plotting in plots, if it is a resistor, it is only on the x-axis. If it's a capacitor, the change is only on the y-axis. Whereas when you are having resistor and capacitor in series, you will find something like this. So now when you are having resistors and capacitor in parallel, if you are doing up the entire maths and you are plotting the real versus the imaginary impedance, then what you have is something like a semicircle. As you can see over here, the equation obtained, if you are solving it up, it is nothing but the equation of the semicircle in this particular case. So generally what is used is a simplified Randall cell to describe any kind of a circuit. So you have a solution resistance, which is this. Then you have a double layer capacitor, and you also have a charge transfer resistance. So this is a very simple circuit. So you have a solution resistance as is shown over here. You have the capacitance because of the double layer formation, and you have this charge transfer resistance happening because of this. It's a very simplified circuit of whatever is happening in this particular simple electrochemical cell. But now if you are having another resistor attached to it, then how this equation changes, you can use the simple mathematical, you can solve it mathematically. You will end up with something like this. So here you have a shift of this R omega. And this plot basically is giving you a complete idea of the different processes which is taking place in that electrochemical cell. You have something which is R omega, which is described over here. This value is nothing but the entire resistance which is happening because of the electrolyte solution, whatever you are having in the cell. The cutting point over here on this point is an addition of this resistance plus the resistance which is coming with the charge transfer, and this height is nothing but it is giving you your capacitance value. So you can see the real part is coming in from the y-axis, the imaginary part is coming in from the real part is coming in from the x-axis, and the imaginary part is coming in from the y-axis. Along with it, as I said, you have some kind of diffusion control also. Mass transfer you have to check it. So mass transfer equation, it is shown over here. Need not go into the details, but we can just look into this particular graph that when the omega is very small, so when your applied frequency is very, very small, in that case, what you have is the equation of a straight line. So you have an equation of a straight line where the slope is equal to 1. And this happens in the area where your frequency is very low. Whereas when you move into the high frequency region, then this particular equation will tell you that the equation looks exactly the same as in the charge transfer process. So when you combine both the high frequency and the low frequency region, what you have is at the high frequency range, the cell process is determined by charge transfer, which is the high frequency region, whereas in the low frequency region, what you have is the cell process is determined by mass transfer or diffusion. So you see the Warburg impedance straight line over here, and this is followed by your entire mass transfer resistance, whatever is happening in the particular cell. So this is how basically a spectrum generally gives. So then once you obtain the spectra, you have to now go for modeling. So you modulate using a network of passive electrical circuit elements, and this network is the so-called equivalent circuit. So in the modeling process, what you do, you get the experimental data, you develop a possible equivalent circuit, adjust it until it fit well, and then you obtain the different parameters as per your fit. And most common softwares which are used for this is ZSync Twin, you have ZView, and you also have Gambly, PKN. So these are the different common software which are generally used to solve the EIS spectrum, to model your EIS spectrum. So an ideal spectrum should look somewhat like this, but you never get it like this. In a lithium-ion battery, if you look into it, these are the different processes, and for a lithium-ion battery, your EIS spectrum is generally going to look like this. So what are these different regions? I have marked it as A, as B, as C, and D. So if you look, region A is basically the single ohmic resistance, and it corresponds to the battery ohmic losses, the resistances of the current collector, active material, electrolyte, and separator. So this point gives you that particular resistance. Then you have the high frequency region B, and this region B is nothing. It is due to the resistance which is coming in due to the formation of your solid electrolyte interface. This is followed by your region C, which is due to the charge transfer, and followed by region D, which is due to mass transport, which is in the low frequency region. This is the mass transport, and this is given by your Wahlberg impedance. So when you give the equivalent circuit, electrical circuit, it is going to look like this. You have a resistance which is corresponding to A region. You have this which is corresponding to your SEI formation. You have this particular equivalent circuit corresponding to your mass transfer, and you have the Wahlberg impedance which is corresponding to the mass transport at the loop. This is how you model, and you can get the entire process which is happening in the battery. So you can have first, before you start cycling, how it's looking. Then you run it for 5 cycles. Then you see how these different resistances are changing, and then you can run it for 1,000 cycles, and again you can check the EIS measurements, and you can see how the different the charge transfer as well as the diffusion, how these different parameters are changing in the battery, and with that you can have a host of knowledge of the electrode material, whatever you're using, whether it's a good material or whether it is which can be practically used or it is not really functioning well. So battery life, so most lithium-ion batteries, it should not be charged at ambient temperatures below 0 degrees or above 45 to 50 degrees centigrade. This is from safety point of view. Because charging at high temperatures will decrease cycle life and it may present a safety hazard. Charging at low temperature, what it does, it leads to the growth of lithium metal dendrites. So you can have an internal short circuit. So it will destroy the battery. Potentially, charger can cause fire. Batteries should be ideally stored at room temperature and at 20 to 40% state of charge. You generally don't want to store battery while fully charged or in elevated temperatures, because this puts a lot of stress on the cell. When it's fully charged, what happens is, as you know, that all your lithium is extracted from the cathode and it is put in the anode, that is the graphite. So it makes a very structure is not very stable in that. So you increase the amount of energy available for thermal running should an accident. So it is better to not really store batteries at full charge. So there are a lot of degradation mechanisms in the battery, and how that the result, whatever is forming, that can help you have an idea of the effect which is leading to that particular thing. So if you have an impedance rise in the battery, it means that there is a change in porosity. It can be a decrease in the electrode surface area. You can have an oxidation of the conductive additive. You can have current collector corrosion. All these factors lead to an impedance rise. So similarly, there are many other factors which will show different kind of effect in your ultimate battery performance. And you can actually find out what is happening in the dynamic changes, what are happening in the battery while it is charging and discharging. So coming to energy density versus power density, once again, if you remember what I had told you, the batteries are good for energy density, but there are supercapacitors which are very good for power density. The supercapacitor part. So what is basically a capacitor? So now finish the battery portion, we are moving to capacitors. So we'll talk about supercapacitors, but before that, let's have a little bit idea about what electrolytic normal capacitors are. So you have two parallel plates which has a dielectric in between. Most common dielectric is there. So capacitance is limited by the flat surface area and the dielectric properties, and capacitance is given by epsilon R, epsilon is equal to A by D. C is the capacitance, A is the area of the electrode, then epsilon R is the relative static permittivity, that's the dielectric constant of a material, epsilon 0 is the permittivity of the space, and D is the distance between these two plates. So this is how you get capacitance in case of normal capacitance, and the capacitance is generally within the range of a few microfarads. So what is the history of supercapacitor? This electric double layer capacitor, this was first noticed in 1957 by General Electric. Then Standard Oil of Ohio discovered this effect in 1966. And then Standard Oil of Ohio gave the licensing to OEC in 1978, marketed the product and named it as a supercapacitor. So as you can see over here, as you can see, the global market size of supercapacitors in 2020 has increased manifold compared to maybe just 10 years back. Supercapacitors has come on very nice in the market because of their very high power density. So what is a supercapacitor? So the energy storage in supercapacitors is mainly in the interface between the electrode and the electrolyte. So this interface between the electrode and electrolyte is the main reason that energy storage happens. This energy storage method has a great relationship with the electrode materials which is used. So what is the basic principle? Is to store electric energy through the electric double layer capacitance formed by the charge separation on the interface between the electrolyte and the bath solution. And why it can achieve higher capacitance is because thinner dielectric and there is a higher surface area of the electrode. So we are using a shorter distance, so D value is decreasing, so C is increasing, and on top of that we are increasing the A. So very simple concept, but so this concept can only be applied when you have really good materials. So in supercapacitors compared to capacitors, the capacitance is in the farad range and they store more energy than the electrolytic capacitors. They have very low leakage current. They are suitable for many applications which are operating between 1.8 to 2.5 volts. And the life of a supercapacitor is very high, it's around 10 to 20 years. There might be some loss in the capacity from 100 to 80% in 8 to 10 years, but the life is almost up to 10 to 20 years. So with 80 to 70% capacity, it can go up to almost 20 years. Very high time. So basic difference between capacitors and supercapacitors when you are drawing it circuit diagram, as you can see over here. So in supercapacitors, if you look, this is the very high surface area. So it is very much material driven, what kind of electrode material you are using, and also it's kind of fabrication oriented, because how less a distance, how short a distance you can have between these two groups. So there are different kinds of supercapacitors. There are electrochemical double layer capacitors. So here the mechanism is electrostatic ion absorption, desorption at the interface of electrode and electrolyte. That's an electrostatic ion absorption and desorption in case of electrochemical double layer capacitors. And then you have something which is called single capacitors. So here a reversible Faraday redox reaction happens between electrolyte ions and electroactive materials. And in between these two, the name as it suggests is hybrid capacitors. So here you have both types. So you have electrochemical double in absorption, desorption, and you have a reversible Faraday reaction. So redox reaction is also there, and absorption, desorption is also there. That's a hybrid capacitor. So what are the charge storage systems? So electrochemical double layer capacitors, they store energy using ion absorption. So there is no redox reaction happening in this case. So high specific area called the electrode is very important in this case, as you have shown it over here. So you can use non-aqueous as well as aqueous electrolyte, but please remember in case of aqueous electrolyte, capacitance is always more. Different materials you can use carbon aerogel, the low density solid derived from gel. So it is composed of nanometer sized particles covalently bonded together. There's a very high porosity, large surface area, so this is very attractive information of these kind of EDLC kind of supercapacitors. Similarly, activated carbon also is extremely porous with very large surface area. The surface, it resembles like a sponge. You can imagine how the surface area will be. So this is also very important material for EDLC. You can use carbon nanotubes. Replaces activated charcoal with carbon nanotubes. So it dramatically increases the effective area of the electrodes and greatly increases the power density. And for the pseudocapacitors, what you have is the redox reaction needs to occur at the surface of the active material, and here the active materials are mostly metal oxides like ruthenium oxide, manganese oxide, iron oxide, and you can also have conducting polymers like polyaniline, polypyrrole, polythiophene, etc. So the capacity in case of conducting polymers is 30 to 40 milliampere hour per gram with the nominal voltage, whereas for the metal oxide it is around 1400 farads per gram. The nominal voltage is 1.2 volts. So these are the different charge storage systems which you are having in case of pseudocapacitors. So electrode materials for supercapacitors, in the research, the stage 1 was mostly material utilizing double layer capacitors. Stage 2 to 1971, it was materials which utilized supercapacitors. Stage 3, that is from 1992 onward, which we have is for composites that combine both double layer as well as supercapacitors. So the difference between rechargeable batteries and supercapacitors, if you look into it, you'll find that in this particular case, the charging time for an electrochemical capacitor is 70% is charged in seconds. In case of battery, the charging can go up to hours. Discharge time is very short. Battery discharge time is very long. Charge discharge cycles, huge number of cycles, which can go from 10,000 cycles to 100,000 cycles. Whereas in a battery, definitely this value is less, but current LIDs are about 5,000 cycles. Pollutants in this case is not so battery, there can be metals. But obviously, the electrochemical capacitor, as you can see, the energy density is not high, but power density is very high. So for many of the applications, they have complementary applications, batteries and supercapacitors, and both are having a lot of applications right now. So if you see rechargeable batteries versus supercapacitors, as I said, it has this one, supercapacitors, a higher power density, much faster charge and discharge rate, is environmentally friendly, extremely low internal resistance, very high efficiency, and it has an over a million charge discharge. What are the applications for supercapacitors? They are used as backup for uninterruptible power supplies. It has lightweight power supplies for small aircraft. It provides short duration power for various vehicle systems, such as for braking and for steering. Then it is used to absorb power during short periods of generation, that is for regenerative braking. We can use supercapacitors, and also extend range and battery life in hybrid electric vehicles. So you can use a battery and supercapacitor in conjunction to have better energy storage technology. So like hybrid electric vehicle, the CSIRO in Australia, which is the National Science Agency, they have developed an ultra battery, which is combining a supercapacitor and a lead acid battery in a single unit. So it gives almost 4 times longer life cycle, 50% more power, and is 70% cheaper than batteries, which are normally used in hybrid electric vehicles. So it's a lot of applications of supercapacitors. A very short overview of fuel cells, because we are talking about electrochemical energy storage devices, so we call it about fuel cell. What is a fuel cell? It is an electrochemical device which converts chemicals like hydrogen and oxygen into water, and it produces electricity in the process. What is the advantage? As long as the reactants, that hydrogen and oxygen, they are supplied to the fuel cell, it continuously produce electricity, they never go there, like conventional batteries. So you keep on producing the fuel, should keep on producing electricity. So there are different types of fuel cells. This is based on the type of the electrolyte which is used. You can have alkaline fuel cell, you can have phosphoric acid fuel cell, you can have polymer electrolyte membrane fuel cells, you can have molten carbonate fuel cell and solid oxide fuel cells. These are all based on the different types of electrolytes which are used in the fuel cell. So these are the types depending on the electrolyte used. Then you can also have different types of fuel cells based on the types of the fuel and oxidant. You can have hydrogen oxygen fuel cell. You can have hydrogen rich gas air fuel cell. So in one side it's the hydrogen moving, the other side it is the air. Then you can have ammonia air fuel cell. You can have syngas air fuel cell. You can also have hydrocarbon air fuel cell. And there are also certain fuel cells which are based on operating temperatures also. So if you look into how these different fuel cells, the classification of fuel cells, suppose we take a polymer electrolyte fuel cell. So here the electrolyte is a polymer membrane. The operating temperature you see is from 60 to 140 degrees. The anode is hydrogen, the cathode is oxygen. And the electrode reactions are also shown. Similarly, if I take a solid oxide fuel cell, that is SOFC, in that case, the electrolyte uses yttria stabilized zirconium. The operating temperature is very high, it is 1000 degrees centigrade. The anode is hydrogen with an oxide and the cathode is lithium. So different types of fuel cell. The alkaline fuel cell, again, you see the electrolyte which is used is potassium hydroxide. The operating temperature is 150 to 200 degrees centigrade. And the anode and the cathode reactions, the corresponding anode and the cathode reactions are shown. So how the fuel cell operates? So over here, this is a solid oxide fuel cell which I have shown. So here what you use is a solid ceramic electrolyte like zirconium oxide stabilized with yttrium oxide instead of a liquid. And as I said, the operating temperature is very high, around 800 to 1000 degrees centigrade. So you have a cathode, an anode, and an electrolyte which is sandwiched between the cathode and the anode. So oxygen from the air, it is flowing through the cathode. Then hydrogen, a fuel gas which is containing hydrogen, it is flowing past the anode. So ultimately what is happening over here, the hydrogen and the oxygen, they are combining, they are leading to formation of water, and the water, it will react with the fuel, carbon dioxide and the electrons from the electrochemical reaction will flow from the anode to an external cell. So ultimately what is happening, continuously if you put in hydrogen and oxygen, continuous electricity is getting generated. This is the ideal resource. Similarly, when you are having a polymer electrolytic membrane fuel cell, the electrodes, they are separated by a polymer membrane. Right? Each of the electrodes is coated on one side with a thin platinum catalyst fluid, as you can see over here. And the electrodes, catalyst and membrane, they form a membrane electrode assembly. Hydrogen and air are supplied on either side, as you can see over here. Through channels, they flow through the channels and form in the flow. So what are the advantages of fuel cell? They have very high efficiency, they are modular, they are quiet, non-polluting, combined heat and power, they are load flexible. So currently fuel cells using methanol and oxygen are being developed. They are used extensively in the space program as sources of direct DC power, and they are also very efficient, capable of providing hundreds of kilowatts of power. So with this, we come to an end of this particular lecture. So we have discussed all the different types of energy materials, the electrochemical energy storage in particular. We talked extensively about batteries, the different concepts which goes in batteries. We have covered how lithium-ion batteries came into the picture, cathode materials, anode materials, cell fabrication, cell characterization, different techniques. And then we had some short nuggets of capacitor, how the capacitor functions, supercapacitors function, and how the fuel cells contribute to energy materials, energy storage. So if you have any questions, I can take it up right now. You can put it in the chat box. Okay, so if there are no questions, then very good evening to all of you, and all those who will be viewing later, a very good day to you. And later on, if you are having any questions, you can always email me. So you can always directly email me. Later on this after this. Thank you.